Welcome to the fifth video, an introduction to quantum field theory following the textbook No Nonsense Quantum Field Theory. This is going to be on spinor fields, and hopefully it will also clear up some of the confusing stuff from video 4.5. So it is necessary to introduce the concept of contra and covariant Weyl spinors. So it's necessary to introduce contra and covariance or variant spinors, specifically Weyl spinors. So we're going to give a little bit of motivation for why we need to do this. First, we're going to look in the algebra of physical space. In the algebra of physical space, there are left-handed, and right-handed Weyl spinors. And we're going to consider some of these. So suppose you have two general elements in this algebra, then you can construct a left spinor. Here is G times F plus, or this is just, this is a projector given by this right here. And then we'll also have F minus, which will have a minus sign right there. And we can define a right Weyl spinor as so. So the reason why I chose different G and H is just so that you know that the coefficients here are different. The coefficients of these spinors are different. So these are different spinors, but this is a left-handed spinor and this is a right-handed spinor. I could have also I could have multiplied instead of F plus, I could have used F minus over here, and that would have made this CR, and this would have made this A to R, or A to L, but I just am doing it this way, just so that we have a left spinor, which we know has different components from this right spinor. And then through grade involution, so right here, through, I don't even put that, I can just put grade involution, which in quantum mechanics, in the algebra of physical space, is the same thing as applying parity. So um, right here, this is grade involution. It's when it negates all vectors and all trivectors. And it's denoted with this little minus superscript. So we perform grade involution, and that gives us different types of spinors. So we get, this becomes a right spinor, which is equal to the grade involution of CL. And similarly, we get a left spinor here, which is given by the grade involution of R. So we see that we can have left and right spinors, and they are related to each other by grade involution. There are also corresponding dual spinors. There are corresponding dual spinors. And these are created by having, or first you have your left spinner, and that maps to sigma x times this. And this is Clifford conjugation. Clifford conjugation is applying both grade involution and reversion, which you see minus plus minus, plus minus goes to minus, minus minus goes to plus. This is what Clifford conjugation does. And the same process is used for right spinners, which I will, just for sake of. So these are the ways to map from the left spinner to a dual left spinner and a right spinner to a dual right spinner. Now, there's something we you don't need to know what this is right now. It's something that will come up, and when it comes up, it will be given physical interpretation then. But for now, it's called the spinor product, which is, if you want to learn more about it, it's a symplectic product, or more accurately called a symplectic form. And the spinor product is always between a dual spinner and a spinner. So it's always between a dual spinner and a spinner. And it's just the projection, or it's the multiplication of them and the projection of it onto the scalar part. And there's a property of spinor products, and this is actually really a property of symplectic forms, is that if you're taking the product of two things that are the same, then the projection onto the scalars needs to be zero. And there's an equivalent property for right spinners, which, hang on. So for right spinners, there's an equivalent property. They have to be zero. But you can also consider the product between between a left spinner and a right spinner by m- by changing one of these into by first changing a left spinner into a right spinner, and then you can consider this right spinner's product with this right spinner. So there is, and you can do this, where go to sigma x, and transform transform this right spinner into a left spinner, and then so what's happening here is it transforms this right spinner into a left spinner through parity, and then through the Clifford conjugation and sigma x, it becomes a dual left spinner. And then you can consider its product with the left spinner here. And there's an equivalent thing you can do for right spinners. When what's happening here is that the left spinner is being made into a right spinner, and then the right spinner is being mapped onto is becoming a dual right spinner. right spinner, and then it considers that dual right spinner with the right spinner here. It becomes a product. So when we have spinners interacting in forms of products, these are the forms in which they interact. Clearly, there exist four, that looks like four, this isn't a word. There are four kind of modes for vial spinners, of which we must keep track. And they are the left and the right, the dual left and the dual right. And these are, of course, related by parity. These are related by parity. That's just parity, parity. Yeah, these are just related by parity. And right here, going down is sigma x, and then going up, sigma x, like this. And you'll see the reason why we have this is, say a dual, we have a dual spinner right here, a dual left spinner. Well then, if we do this, then that's just this. So to make it, if we want to make it equal to this, we need to apply two Clifford conjugations to cancel out. And so applying this again cancels out the sigma x here. Then applying this here again cancels out the Clifford conjugation. So it goes back. This goes from left to dual. This goes from dual to left. And you have this right here is actually the same. So I'm just going to clean it up. Put it like this. So you can see that things are related through parity and through going to the normal ones to the dual ones. Well, the textbook that we are using the textbook uses Van or Van der Werden convention, where you have a spinner with a lower index, a spinner with a lower index that is dotted, a spinner with an upper index, and a spinner with an upper index that is dotted. And these end up being related or these are related in the same way. And so spinners that look like this, these are called undotted. These are called dotted. These are called covariant. These are called contravariant. So you can have a contravariant undotted or dotted spinner and a contravariant, or just say contra or co. Covariant, undotted, dotted, contravariant, undotted, dotted. And contravariant or covariant corresponds to the normal left and right, and contravariant corresponds to the contravariant corresponds to shoot the the dual spinners. And this is the convention that is used in the textbook. They don't actually know that they're dealing with geometric algebra, so they actually just define this kind of in a vacuum. But this is what the definition really comes from. It's because geometric algebra has this pattern, so they end up defining things with the pattern. Now let's talk about what the actual components of spinners represent. So you can have spin up, can be left-handed. You can have spin down, which is left-handed. You can have spin up, which is right-handed, and you can have spin down, which is right-handed. Well, these are typically written as column matrices, and typically associated. So you have left, left, right, right. So the top component in the left is spin up, top component in the right is spin up, bottom components are both spin down in both left and right. But what part of these, because how does this correspond to the matrix representation up here? Because you can see that you can have this, oh, I don't know, you can have spin up, spin up, spin down, or spin down, spin up, like however you're defining it. Well, here's actually how it's defined. How or what the correspondence is. Now you might be confused. There's a one here and there's a one here. So how on earth is it that they both that they can distinguish themselves in the math? Well, typically you don't actually add these matrices together. They're always there in products. So you end up with something that looks like a column spinner here, and then something that looks like a row spinner here. And then you end up multiplying those together. And we'll see exactly why they are defined this way. Why spin up is defined in the same position that spin down is defined for left. So this is because in the normal quantum field theory um, conventions, you can have a left Weyl um, spinor field, which is defined by the position, spacetime position. And it has some component, some left-handed component in the spin up direction, some spin down direction, And there's an identical definition for right vial spinor fields. And there is something called a Dirac spinor field. Doesn't look like it says Dirac. Dirac spinor field. This is typically written with a capital C, and it has the different spinners. It has a left spinner in the top and a bottom or right spinner in the bottom, which looks like this. So they actually, in the Dirac spinner, they have a covariant and a contravariant spinner. And you might be wondering, why do they have a covariant and a contravariant here? Well, this is actually because it uses covariant dotted, which is a, come on, it's not erasing. There we go. Left vial spinner and a contravariant. Oh, this should say undotted. A contravariant dotted, which is a dual right spinner, because those are what interact in the spinor product. So remember how the spinor product always has dual interacting with not dual? Well, it's because they want to be able to take this and have them interact without having to uh, perform dual operations or raising or lowering indices. And the way that this is typically done outside of geometric algebra is by performing complex conjugation, which is the same as the grade involution. And then that just makes it like this, which is the corresponds to corresponds to taking the right corresponds to this product. So yeah, these are the basics of spinor fields, and their notation.